Hi, guys. All right, so for our notes today, we're going to be picking up on page number 7. Hoping this video turns out okay. I'm filming from a different computer right now, so my apologies if this is a little funky. Hopefully it'll work. All right, so we are again on page number 7. Again, this particular video is going to be a little bit more vocabulary heavy than is typical. It's just there's a lot of terminology we kind of have to get out of the way up front so that for the rest of the year we can talk about these things. So diving right in, let us talk about what is an element. So an element is the simplest form of matter. It cannot be broken down by chemical means. So think of elements like being the building blocks, all right? The Legos that make everything else. You can't change the Legos, right? No one is sawing Legos in half or gluing them together to make other Lego pieces. They're what you have to make, and you form them in different combinations to make literally everything else. But in a chemical reaction, you do not change the elements. If you're starting with 6 atoms of carbon, you will end with 6 atoms of carbon. If you start with 17 atoms of hydrogen, you will end with 17 atoms of hydrogen. So anything that's on the periodic table is considered an element. So things like oxygen, hydrogen, and iron. Now there are 7 elements that are special. And these particular elements, I'm actually going to highlight this right here, if I can do that, are known as diatomic elements. Now the prefix di means 2. So a diatomic element, the word diatomic literally translates as a 2-atom element. These 7 different elements can never be alone. They are always going to either be with other elements and form what's known as a compound, or if you do have this pure element, it's going to find another atom of itself and join up to form a pair. So for example, hydrogen, it's never a single atom of hydrogen. It's always H2, 2 atoms of hydrogen bonded together to make hydrogen gas. Same thing with oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So these 7 different elements, the one way to remember them is to think of the word Hofbrinkel, and that'll remind you of the 7 different elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. And then also, if you were to look at the periodic table, and where these elements are on the periodic table. So I'm just going to sketch out a periodic table really quickly. Looks something kind of like that. When you look at where these elements are, your hydrogen is in this corner here, and then the other 6 actually form the number 7 on your periodic table. So if you have a periodic table handy, you can kind of see where these elements are. So take a look, take out your periodic table, scope out where these 7 different elements are found, and you'll see there's sort of a pattern to where you're going to find them. Now our next word is compound. A compound is a substance that contains 2 or more elements combined chemically, meaning they are bonded together. Okay, so some examples of things like this, that NaCl, where we have an atom of sodium, an atom of chlorine, they are bonded together, you have sodium chloride, which is salt. Another example might be something like H2O, where they are bonded together, 2 atoms of hydrogen, 1 atom of oxygen to form water. CO2, carbon dioxide, 1 atom of carbon, 2 atoms of oxygen bonded together. Maybe you remember from biology, C6H12O6, which is glucose. 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen bonded together. That is a compound. Now, both elements and compounds are considered to be substances, meaning if we take back in our notes, back up where we talked about substances, which was way back on the very first page, a substance is matter that has a uniform composition throughout the universe. So no matter where you find an element, it is going to be chemically identical. No matter where you find a particular compound, it will be chemically identical. Water is always H2O, whether it's from Lake Erie, the Amazon rainforest, or Mars. That's what makes it water. When a compound is composed of two and only two different elements, it is known as a binary compound. So water is an example of a binary compound. Carbon dioxide is an example of a binary compound. If you have a compound that has three different elements, it's known as a tertiary compound. So like glucose, C6H12O6, is tertiary. When you have compounds changing into other compounds, that is when you have a chemical change. There is a change that produces matter with a different composition than the original matter. You are in a chemical change. You are taking a substance, breaking the atoms apart, and rearranging them to form new substances. That's a chemical change. All right, so to put all of these different words into context a little bit, this first block here, we're going to have matter. Now remember, matter is anything that has mass and takes up space, okay? So pretty big category. All matter can be subdivided into a substance, which has a definite composition throughout the universe. So water is water no matter where you find it, for example. Or you can have a mixture. A mixture, so we'll say mixture of substances, where the composition can vary. I gave the example of if I ask everyone in the classroom to make salt water, we're going to wind up with 27 different varieties of salt water because everyone's going to use different amounts of salt and different amounts of water. So the percentages that make up that mixture can vary, even though they are all salt water. All right, heading back to the substance side, what we just talked about is substances can be separated into two categories. You can have substances which are elements, meaning it's, one, it's the simplest form of matter. It's the building block. It's one pure thing. Or you can have compounds where we take those building blocks, those elements, and we put them together in different arrangements to form things like H2O or CO2. On our mixture side of things, we have our homogeneous or homogeneous, again, however you prefer to say that, also known as a solution. Or we have heterogeneous mixtures, where you're the difference here being in a homogeneous solution or mixture, throughout that particular sample, it's uniform throughout. So the first bite is the same as the last bite. Whereas a heterogeneous mixture, that if you have like a bucket of something, every ladleful will be slightly different in terms of its composition that makes it up, okay? All right, just to finish off this section, guys, symbols and formulas. Symbols. So all elements have symbols, right? It's either one or two letters. The first letter in an element symbol is always a capital letter. The second letter is always lowercase. So some examples of this might include things like carbon, which is just the letter C. We might have something like helium, He. Now I want to just briefly mention on your periodic table, you might notice these symbols here that have three letters. This periodic table was actually published in 2011. So this is 10 years old. This periodic table that's in your reference tables is over a decade old. In the 10 years since they published this table, these elements that have the three-letter symbols have actually been renamed. They've gotten permanent names, and now they have only two-letter symbols, okay? But I do want to make sure that everyone's aware that when we're talking about an element symbol, it's always going to be a capital letter followed by a lowercase letter. So for example, CO is the element cobalt. If I instead say CO, where both the C and the O are capitalized, this is actually a compound made up of carbon and oxygen. So this would actually be carbon monoxide. All right, so capitalization is super important. Cobalt, on the other hand, is an element. So cobalt, which I'll say is an element, found on the periodic table. Okay, so be very deliberate in whether you're making a capital letter or a lowercase letter, because it does matter. Formulas are when we start to take all these different element symbols and put them together. So for example, I think everyone is aware, water is H2O, 2 hydrogen atoms, 1 oxygen atom bonded together to make water. Chemical reaction is when one or more substances rearrange their atoms to form new substances. So for example, I might have hydrogen gas, which is H2, combining with iodine gas, which is I2, react to form, and then we get 2 molecules of HI, hydrogen iodide, okay? So everything that is to the left of this arrow are known as your reactants. This is the starting substances. It's what you begin the reaction with. Everything to the right of the arrow are your products. These are your formed substances. It's what you're ending with. Okay. And all chemical reactions or physical changes like boiling, freezing, melting, condensing, whatever, have to obey what's known as the law of conservation of mass. That says that in any physical change or chemical reaction, mass is neither created nor destroyed. So the mass of the reactants must equal the mass of the products. Okay? So think about that for a minute. When you burn a piece of wood in a fireplace, you are taking that wood, you are adding oxygen to it, and it is combusting and forming carbon dioxide and water vapor, and there's some ash and all that kind of stuff. If you were to do this combustion reaction in a closed chamber where the smoke is contained and everything stays contained, it doesn't go up a chimney and leaves, the mass of all the smoke and the ash and everything that is produced at the end is equal to the mass of the log, okay? You don't lose mass during a chemical reaction, and you don't create mass. When that does, the exception being nuclear reactions. This is how atomic bombs work. We take something like uranium, and we take a tiny little bit of that mass of the uranium, and we convert it into pure energy. E equals mc squared, that famous formula by Einstein. But that's not a regular chemical reaction. That's a nuclear bomb. It's a nuclear reaction. So 99.9% of the time when we're talking about stuff we're doing in this class, mass is conserved. The amount of mass that you start with is equal to the amount of mass that you end with. And with that, guys, I'm going to stop there. This is a nice short one. As always, let me know if you have any questions, and I'll see you in class. Bye.